missing. Okay, so once we decided what to draw, then we try to impute those that are left, those that we believe that it's worth somehow of filling because we want to take advantage of the data. So we can do this with different procedures. For example, we can do this with simple imputation, and in the case of categorical data, you can impute with codes. But in the case of numerical data, you can impute by finding some type of mean or median. And if you go for the median, it has the advantages that somehow you discard the influence of outliers, right? Because mean is considering everything, but the median, of course, for numerical features, right? We can only use these mathematical operations with numbers. The median somehow discards the outlier because it takes into account what repeats the most, right? So these type of decisions are actually important, as you can see, for the accuracy that you will obtain at the end. But you can also use more advanced approaches. You can, for example, try to fill those missing values by finding, let's say, a median, but for samples that are somehow related to the sample that you are filling the missing value. What does this mean? This means that if you know that your sample belongs, let's say, to a type of building, then you only select the mean of the feature for this type of building. This somehow creates a more robust type of filling. And there are also even more advanced methods where you can, for example, impute by using a machine learning method. You can try to train this classifiers, for example, in this case, I'm using the nearest neighbor. And then you impute your values by using values of samples that are somehow more similar to you as given by the classifier. So I will encourage to use this type of procedures because I believe that they may provide better results in general because they take into account more information when they are filling the missing values. So therefore, this is my preference to use this type of machine learning imputation, but you're free to try the others. And yeah, there are probably even more than the ones I presented, but you can start with this. So let's see also more about the features. So let's analyze the correlation of some of the features. We have these heat maps, and here you can see the darker, the more positive correlated, and if we have a less dark, then it means that features are more negatively correlated. So if we look at this part, we see that, for example, average temperature is correlated with many features related somehow to weather, right? And this happens also in other parts of features related to weather. They seem to be somehow correlated. And this makes sense, of course. We understand that. Therefore, it may be good to also analyze what to do with this type of features, because sometimes correlations means that you are repeating information. And if, for example, the information is not actually good, your classifier will be biased to actually learn about this information. And therefore, we don't want that. So we would like also to remove correlations on our data. So this is something to consider. And as you can see, we have more. We have even here a lot of correlation in this variable. So you can decide what to do in these cases. So besides this, I also wanted to somehow plot the distribution of some of the categorical features in this case for the training and the test set to show you how they do not exactly match. So what we see for the distribution of some of the features or variables in the train set is not what we see in the test set, which is the set to which we have to provide these regression values to be evaluated for the competition, right? To find our position in the leaderboard. So here I presented some code for plotting this variable, the state factor, the building classification, and the year factor, right? So we can already see strange things. We can already see, for example, that state 6 is the one with more samples for our training set. So in this case, I'm plotting the training data. And we can also see that we have from 1 to 6 year factor. Of course, we know that the year factor is somehow an anonymized version of some year that we don't have the value. We only have codes representing the year factor, but then we see that we have 6 in our training data, right? And then when we go to the test data, we see a different thing. So we see that now, for example, state factor 6 is completely missing for the test data, right? So it was the one most represented for the training data, but then it's completely missing for the test data. But we also see that for the distribution of the other states, they also don't match too well for the test sets. And we see, for example, the building classification, we have more residential in the training data, and then we have more commercial in the test data. And for the year factor, we see that we only have 1 year factor for the test data, right? We don't have from 1 to 6. Therefore, we have to carefully analyze what does this mean for our pipelines, right? It's probably, in my opinion, I believe that probably they measure these variables in some of the first 6 years, and then like interpreting this as a time series, they want to see what happens in the 7th years. So we don't know. Well, what we can see and what we know is that there is a mismatch for some of the features, and this can indeed influence the results of our regression. Therefore, we can try to think about strategies. What do we do? Do we create different classifiers, for example, for each of the states, for each of the year factors? I don't know. So this is something that probably should be considered when creating your regression methods. So besides this, I also want to show some box plots for different variables, because this is interesting in the sense that when we look at the box plots, we see that there are outliers for some of the variables. So if you look at the floor area, most of the data lies in this region, in the yellow region, right? And these isolated points represent outliers, also for the other variables. So even for our target variable, the site energy use, we have a lot of outliers outside of this yellow zone. So here we have most of our data, and then this data somehow does not fit well with the data distribution, and this is a long tail. This is what is called a long tail. So we have most of our data in one region, and then we have this. So what do we do with this in all the variables? So do we drop these instances? So it also depends on how this behaves for the test sets, right? So when we look at the test set, for some of them, then we don't have missing values anymore. Well, at least not that much. We have some of them, like, I don't know, maybe 5, 6, also in other variables. But we can see that it's not the same as we see in the training set. So this may also be interesting to understand what to do. So should we drop those? Should we create a different classifier for those? I don't know. Well, when I say classifier, I mean regression, right? So let's look at other type of visualizations. For example, we have the site energy use, our target variables, and we have the year factors. And we can see that, at least using the order that is given in the data, it seems that for bigger year factor, we have probably lower site energy use. I think, yeah, it seems a bit lower, right? So this may also be somehow taken into account when developing your procedures. And if we look at this site energy use for the state factor, we also see that there is a difference for the different states. And we see that the state with more training data, we already saw that, it also has somehow a higher type of site energy use. So this is also interesting information. And when we look at the energy star rating, we can also see that there is a similar trend to what we see in the site energy use, but it's somehow flipped. And we will see more about the relationship between the site energy use and the energy star rating. But now we can see that for the state 6, we also see a kind of lower energy star rating. And for those states who had a lower site energy use, we see now a larger somehow energy star rating. So they seem to have a type of inverse relation, and we will see more in other plots. So some considerations after this analysis that can be somehow provided is that, yeah, for the training data, we have year factors from 1 to 6, and then for the test data, we have a different one. We can see that there are outliers from the different plots that we presented, at least outlier values for those features. So this may not mean that the whole sample is an outlier, but maybe these outliers can somehow affect negatively the performance of the methods. We can see that the distribution of some of the features is different from the training to the test set. We can see that training set is mostly about state factor 6, and then in the test set, we don't have that state factor. So there is a lot of mismatch between the training's data distribution and the test set distribution. So we see that also some of the features are correlated. What does this mean? It depends on how you want to process correlated data. It may mean that we should remove them. It may mean that we should somehow try to combine them in only one. And yeah, we have our target variable that seems to decrease per year, at least for the order that was given in the data. And yeah, state 6 seems to be the one with highest mean. Yeah, what does this mean? It depends. It depends. It may be that you want to create, I don't know, a classifier for the training data, but you know that your training data is biased toward the highest mean. So then you may have to do some pre-processing for your results on the test data, right? So this is a technique that is used for other Kaggle competitions. Once you have your results, your prediction results, your regression results, maybe you can slightly decrease or increase the values of the results based on the distribution, for example, of the training data, because you know that this mean is biased somehow, the mean of the training data. Therefore, you have to see what happened with the mean of your predictions, right? So yeah, I have other plots, for example, that you can use. I use it here for the floor area versus the site energy usage, but you can also use them for other type of plots. So we see, yeah, we see how they interact, and I also show somehow the distributions here, and you can see that, for example, for floor area, most of the data lies here, and for site energy usage, also most of the data lies here. So it seems that also lower floor area is related to lower site energy usage, which seems strange because, yeah, I would thought that it has to do with higher floor area, but yeah, it's just what I think. It always depends on what the data is reflecting, what the data is telling you. So therefore, it's good to do this type of visualizations, not only for this, but maybe other type of pairs of variables. So here I'm also loading different variables. In this case, again, the site energy use versus the year built of the building, right? And of course, I'm using a mean of the year built. And we can see this trend. So we don't have too much information for the first year, at least not too much of a pattern that we can exploit. But then when you look at the year built for the last years, then we see a drop in site energy usage. This makes sense, of course, because probably you then are buying new equipment which are more efficient, right? And probably all the infrastructure of the building is also with a more efficient type of mechanism. So it makes a lot of sense. But even maybe because apartments are smaller, who knows? Who knows what can influence? But we definitely see a drop in energy use for the last for those buildings we have a more recent year of build. So yeah, let's also plot the energy usage with this energy star rating. We already saw that there seems to be a relationship between both, right? And it makes sense because we use this type of ratings to say how energy efficient should your apartment house be, right? We usually use this because they are computed with all the information that says how energy efficient you should be. And of course, this is correlated somehow to what the actual energy use is, but in a different way, because we measure the energy use, of course, the higher, the more energy use you have, but the star rating seems to be different. The lower, the less energy use you have, something like that. But yeah, the fact is that there is inflation, and this can also be exploited somehow for your methods. And probably this would be one of the variables which more important for your regressors, right? Because it seems to have a relationship with the target variable. So yeah, these are the considerations that we have from this analysis. And now let's have a look already to the procedures for handling the data. So we have some insights. Now we know that we can leverage those insights in some way, but what to do in our processes. So we start now with encoding the features because we want to be able to send this as input for classifiers for regressors. And right now they are given in codes that we need to transform in a way that we can use them. So we do this by encoding them. In this case, I am just transforming labels from ABC, let's say, to 1 to 3. So two numbers usually continuous, and they can be used for the decision trees, for other classifiers. And then we want to remove also features with low variance. This means that if a feature is kind of constant for all the sample, this may not represent too much information for our procedures, and therefore this also can create bias, because then procedures may use this, and this is not actually presenting variability that is important into account, right? So we can also remove those columns with low variation, and then we decide to remove correlations. I use a very high number here, but you can decide what you want to do. You can also try to lower this threshold and see if it makes sense to remove all those variables that are somehow correlated given the threshold. And we drop those columns that do not represent anything, do not represent useful information for our methods. Of course, the identifiers and the site energy use, we will not consider it for the training set. Of course, we will use it later as the target of our procedures, but the training set does not actually need this variable to train the methods. Then, of course, we scale up our numerical features. Of course, this depends on the method. If you're going to use decision trees, they are really robust to scaling issues. But other procedures, such as those based on distances, especially those based on distances, the nearest neighbor, maybe even deep neural networks, they are very sensitive to the scale on which the features operate. Therefore, we want to somehow normalize each feature to be in a similar scale. So for example, between 0 and 1, between -1 and 1, because then one feature is not dominating over the other features. And we don't want that. We want to consider all those features with the same weight, and then classifiers somehow find the different actual ways that they should use. So it is a good practice to do this, especially if you don't know which classifiers or regressors you will use at later stages. So we always try to do that. And we know that if we don't do it, probably it will not affect classifiers or regressors based on decision trees. They are really robust to scaling, but always a good practice to do it. In this case, I'm doing it for this challenge. And then we enter also in issues related to feature engineering. This is something that you should always consider for Kaggle competitions. Usually, especially in data competitions, feature engineering provides a high value. Feature engineering can actually represent the difference between a very bad position in the leaderboard and a good position. So my advice is to look at feature engineering. I'm bringing here an example of one way to do this. So here I'm creating a new feature, and I call it energy facility, and it is the result of dividing the floor area by energy star rating, for example, because I believe that there may be this relationship may provide information, and you can do this, of course, for both the training and the testing. But this is just my idea. There are others. For example, I was thinking in the possibility of using the weather data. Let's say finding slopes for the weather data for the different months of the year. This may provide relevant information because this says, for example, for a lower slope, it may mean that you have similar weather in your state, and this may mean that you don't need so much energy consumption. But for different slope, when you have a very cold winter season and then very hot summer, this may mean that you need to consume more energy, right? Because then you need your heating, and you may also need your air conditioning in the summer. So those things are not provided in the training data, but can somehow be inferred by how we analyze this data. And everybody knows about weather, about how weather behaves. So this is something that you don't actually need to be climate change and energy expert to analyze those issues. So my advice here is to try to come up with different feature engineering. This is an example. There are many more, and it's probably a winning recipe to be able to do a good feature engineering. So besides that, we also have the topic of outlier detection. And as I said, this may somehow influence that your performance may not be good. So this type of steps, they usually constitute parts of your solution. It's not that one of them will provide a huge boost in accuracy, but that the combination of these small design decisions can actually lead you to improve the overall accuracy. It's not that one step will provide you suddenly an amazing solution, but that you should do all these small steps and they will gradually help you to increase your accuracy. So in this case, I'm using also machine learning methods to remove outliers. It is called isolation forest. And I set some threshold, so I will drop just a bit. of my outliers. I don't want to drop too many. And then, yeah, you see how this reflects on your actual training and target. So with this, you continue your pipeline, and then we have also the feature selection step. So feature selection is usually useful, and especially when you have a large set of data, so a large set of variables, I mean, and of course it helps you also remove all those features that do not present relevant information. But the issue here is that you have to be careful, because depending on the feature selection method that you use, then your features can be good, better, or not so good. So it is actually a decision that, yeah, is not easy to make. So you have to decide carefully if you are going to do feature selection, and then which type of feature selection method you will use. So here I present, for example, feature selection by Lasso, which is also a type of regressor. And it is known that the coefficients, when the coefficients of this regression are not 0, then you can use those variables. Then the method is somehow saying that those variables are relevant. And you can select as many as you want. You can select the first 20, the first 30, and so on. And I also leave here a different method, which is called sequential feature selection. And in this case, you have to pass as parameter which type of classification regression method you will use to actually measure the performance of each set of features that the method is testing. So in this case, it starts with one feature, and then it adds the second feature in a way that these two features provide the best results compared to any other pair of features. And then it adds the third feature in a way that this triplet provides the best results compared to any other triplet, and so on, or at least to any other triplet that contains the already selected two variables. And with this, you can also decide how many features you want, so when to stop. So yeah, the accuracy of the set of features depends a lot on the type of feature selection method, but also the criteria to measure how good the features are. So therefore, you have to think really careful what type of feature selection method, what type of criteria you will use to select the features. But it's something that you can also test, and in many occasions with appropriate feature selection methods for the classifiers or regressors that you will use, you can actually have gains in accuracy. So here, for example, I show you which features were selected by this Lasso regressor. And as you can see, we already have our energy star rating. It seems to be a really good feature. And then we have other features. We have the temperature-related features. We have building-related features, and so on. And you can see how the importance is decreasing. And for these features, apparently, this Lasso method, it does not find that they are really relevant for the problem. So after our feature selection, now we have our training set with a reduced probably set of features. So we started in this challenge with 60 features. We will probably end with, let's say, 30 features, right? And we know that these features should be better than having the whole set. Therefore, now what we have to do is to try to train regressors on this data. And not only training regressors, but also analyzing which regressors really make sense to train or to use for our challenge. And if we only use the training data as is given and the test data as is given by the competition, then the methodology will be to train our regressors on the training data and then try to find the predictions for the test data and submit these results to the leaderboard and see what is the accuracy on this data according to the leaderboard, right? Therefore, if we use the data as it is, we cannot know what is the actual accuracy of our regressors before sending the results to the leaderboard. Therefore, it would be good to do something to this training data so we can actually know before sending the results to the leaderboard how good are the regressors that we are using, right? And for this, we usually do strategies related to data splitting, training data splitting, and there are some of them, and in general, we are given our whole training data, and we try to leverage this training data in a way that we can also find a subset for testing and validating our regressors or classifiers. And the simplest strategy is to split it into two sets now. One that we call a training set and one that we call the test or validation set. And it can be even more. We can even have a third set because we may want to use a small set to optimize the parameters of our regressors, and then another set, the one that we call test data, which help us to see what is the performance or the accuracy of our regressors or methods in this data, because this data is not seen in training time. So we train our classifiers with this training data, and then we can see for this test data, what is the accuracy of those trained classifiers. So it is a good practice to have a test set that is not seen in training time to be able to understand what is the accuracy of these classifiers. Because if you use the same trained data, then you are overfitting your regressor. You are just looking at what the regressor used for training. So this is not an indicative of the real performance or accuracy of your method. So a good practice is to never use the training data to understand what is the performance of your method. Although, for example, in these neural network procedures, you will always see how the accuracies are behaving in the different training steps, but that doesn't mean that this is the performance of your classifier for real data that was not seen in training time. And this is what we need. This is what we need. Actually, if you look at the test set that is given to you, you're not using it for training. The test set that the competition gives you is not used at all in training. Well, maybe you can use it as I mentioned, for looking at the distributions to understand what is happening with both sets, because you can do something accordingly. You can then somehow do a post-processing for your predictions, but not for using it in training time. Okay, so this is really important. That's why I try to make emphasis on this part. And there are other options. For example, cross-validation can help you a lot to understand really what is the actual accuracy of your method. And with this procedure, you can rotate your data, and you can always see, you can always use every sample for training. So this is important to know the exact accuracy of your training, of your training model. But in this case, what we want to do is to improve our model. So we want to have a baseline for comparison, and then somehow to improve those baselines, right? And this can be done with this strategy, and that's why this is the one that we're going to use, because what we want is to be able to improve our results. So to compare our regressors with better versions of them, with tuned parameters, and try to find the best result. So we do this here. Now we know that we have a training and a test set for testing the results. So we start training one of our methods, for example, the XGBoost regressor, and we give a set of parameters. These parameters are also really important. So yeah, the optimal thing will be to do a grid search to find the best set of parameters. But we start with parameters that make sense somehow. So the number of estimators, the learning rate, and the depths of these regressors. So we apply the model, we feed the models to our training data, and we predict for our test data. But this test data is not the one given by the competition, but the one that I already selected out of the training set because I want to know what is the performance on this set. So I do have the target variable, the target features for this set. So now I want to compare my predictions to these target real values. And then I use this metric, which is the one given by the competition. They want to know this metric. There are others, but this is the one they are interested in. Therefore, we also use it because we have then a basis for comparison. And I print what is our error in this case. And I can do this also for other models. So I also leave here some source code that you can use to save the model, because if you want to avoid having to compute all the data processing and then only use the results of the classifier and combine it with others, then you can try to save them, classifiers and regressors. And in this case, what I save here is the model, but fitted to the whole training set, because this division of training and testing, we do it to understand performance. But to train our regressors for the competition, we need to use the whole training set, because we are using more data and this increases accuracy of our methods. Therefore, we have our model fitting the whole data and with the target of the whole data. So we have our trained model, and then we try to save it. I did it like this because here, of course, the results are just a set of values, a set of predictions for the target features. Therefore, it is just an array. So I save this array, and we can load it later. We can also use it in a combination, assign it different weights for the results of each of the methods. So here I do the same for a different method, also trying to find a good set of parameters. And I try to look at the results, and I save the model trained on the whole training data. Also for this classifier, so these three methods are usually the ones that perform better in this type of competition. This, of course, sometimes combined with deep networks, but in this specific challenge, I think the networks that I have seen in other notebooks do not perform really well, and they are usually given a very low weight if they are using a combination. But in this case, these three methods seems to have a better performance for this type of competition. This doesn't mean that they are the best methods for every type of data challenge. It just means that for Kaggle data challenges and this type of categorical and numerical feature combined data sets, they seem to provide good results. So I save the three models and then also try to read them back, because this is what we want to do. We train, we save, and at some moment we want to leverage those models. We want to do different type of combinations, and here I combine with these weights depending on how was the accuracy for this validation set that I created. It can also help you give the right weights. And then you have your submission file. You read what is given by them. You assign the prediction values to the variable of interest, and you submit your submission. So this is the score by the method that I show you, the first method, which is the one that I was using. And as you can see, it is still high. We want to lower this score as much as possible, because this is what helps you improve your accuracy and be higher in the leaderboard. So I leave here also the source code for doing a grid search, and this helps you to somehow find the optimal parameters from a set of parameters that you can give to the method, and you just call the grid search with the model and the parameter. And then you can feed it to your data. So the problem with this type of procedures is that they take time. So if you have time, if you have good computational resources, then you can try to use it. If you don't have them, then probably it's better to try to set up by hand the parameters that you need. You try to tune them maybe by running these 2 or 3 times, try to find the best and then use those that you realize perform best. But yeah, if you have resources, probably grid search is a better option. And then we want to train, for example, a combined model. We want to train a voting regression model, and you can leverage the different individual models, and you can use what is called these pipelines also, where you train feature selection for, let's say, one of the models only. And this can be done with these concepts of pipeline in Python. I have our list of models, and then I add to this list each of the models that we have, or the ones that we prefer to use in our combination, and then use some type of voting mechanism. And in this case, we have this voting regressor, we have the weights. Probably we should add a 0 here before this. I'm not really sure how this works, because I usually do it between 0 and 1. And then you feed the whole voting mechanism to your data. Of course, again, if you want to see the accuracy, you can do it for this validation set that we created. But then to train for the competition, you need to train with the whole data. That's why now we do it, we train with this whole data for this combination, and we test for the set given by the competition, and we create our sample solution. So we finish, we submitted our solution, but we can also analyze for the models that we created, what are the feature importances and what are the influences of these features on the outcomes. And for this, we use what is called SHAP values. So I also leave here the links to other notebooks which have a more thorough explanation of these SHAP values, but I added a short visualization of this here. And we have our test set, and we have our SHAP explainer. So we try to fit it to our XGBoost models and to see the results of this SHAP explanation for this XGBoost model. So here it shows us what are the importances of features according to the SHAP values. And again, we see that the energy start seems to be really important, and we have facility types, floor area, and so on. But besides the importances, we can also visualize the impact of these feature values on the outcomes. So we can show also different type of plots, such as the summary plot, which tell us for each of the features, how is the influence on the impact. And I think blue here is a lower impact. So for higher energy star rating, it impacts like negatively in the energy efficiency. And then for lower values of energy star rating, it impacts positively. So I think each of the variables have a different type of relationship with the outcome, with the target variables. In this case, energy star, lower energy star means higher energy usage, and higher energy star means lower site energy usage. But if we look at others, we may find a different thing. If we look at here snowfall, it seems that higher snowfall inches also provide a higher energy usage, and lower provides a lower energy usage. So this is the type of relationship, but also the magnitude. The magnitude for energy star, we see that is much higher than for the other variables. At least energy star and facility type seem to have a higher magnitude of influence, and for the others, we have lower magnitudes of influence, but still we can see the relationship. We can see that lower values relate in some way and higher values relate in a different way, right? So this helps you to understand how the features relate or impact the outcomes, but there are other ways to see that. There are even local explanations that can be used for some cases, especially if you want to know what is happening for specific samples. If you want to know for these samples why the procedure, the machine learning method, is giving me this result, Then you can also look at line explanations, and this can be found in this notebook that I leave here. So I think that's it, and I think the time is probably going. So yeah, I think I should finish here. Questions from you?
Any questions from our audience, our listeners? Okay.
I actually had a question.
Yeah.
In the beginning of your presentation, it was very nice, by the way, but you started to talk about imputation, and I'm a huge fan of imputation. But I was wondering, just thinking about it, you gave an approach that uses machine learning for the imputation, and I wondered, what are the implications of using machine learning for imputation and then putting it back into an AI model or a machine learning model? Then it feels like a circle, yeah, like you're going round and round, using all the variables to estimate it and then putting it back to estimate variables again. So that felt a bit weird. So yeah,
I understand.
Comment on that.
I understand your concerns, but when we use a machine learning method, the idea is that, we will find the values to impute for a given variable, for a given sample based, in this case with the nearest neighbor, on the samples that are closer to this in the feature space, in the sense that they are similar in the other variables. So now we are making an assumption. Of course, we are assuming that the feature value should be similar to feature values of other samples that are similar to your sample. So this is a strong assumption, but this assumption usually holds for this type of machine learning problems. Usually, if there are other samples that are very similar to you in the other features, it's probably that this specific feature that you have to impute also has similar values to the features in the other samples. This is a strong assumption, but usually holds for this type of problem. It will have some impact in the classifiers, especially if the assumption does not hold. You are completely right. But if the assumption holds, we will probably have a very good estimation of the feature value, especially, if the assumption holds combined with the method that we use for imputation. So now we are saying that we are using nearest neighbor, and nearest neighbor, of course, assume it's based on distances, and assume that closeness means that you are probably more similar to me. Closeness in the feature space, in the space generated, of course, by this multidimensional space generated by all the features. So yeah, you're completely right. It will have an influence in the results, but I believe in these cases that, for example, filling missing values with just the mean of the whole set without considering how the other features behave, this is probably more problematic for the result of classifiers, because it is not reflecting reality. It is not at all reflecting reality. I remember in the training last year, we were talking about missing value imputation for height of different genders, of course, of women and men. And for males, the height is probably different than the height for females. And we can see that from data usually. So therefore, one option there was to replace by the mean, but by the mean of your own gender, right? If you were a sample of a female, then you replace by the mean of females. And this made more sense for this data set, because of course, this is an assumption that holds. You can compute it from the data. And also here, if the assumption holds, and it usually holds for many machine learning problems, that the closest you are, then the more similar some of their features may be. So this is something that, yeah, is definitely to consider, and it will definitely impact the results of classifiers.
Thank you.
Thank you for the question.
Thank you. Any questions? We can take one more question probably. You can just unmute yourself if you have any questions.
I have a short question. So can you hear me?
Yes, yes,
Yeah.
yes.
Yeah, thank you very much for the nice presentation, and I also wish you a speedy recovery.
Thank you.
Yeah, and so in the beginning, you also talked about biases and fairness, and I was just wondering, could you please explain a bit more on this aspect, particularly for this solution? What do you or what you wanted to mean by that?
Yes, yes. So bias is usually more clear in classification problems. For example, if we have a class that is overrepresented and we have another class that is represented by just a few samples, then we have usually an imbalance, and our classifiers will be biased towards the class that is overrepresented, right? So here that's more difficult because we don't have classes. What we have are continuous values, right? But still there can be biases because, for example, what I mentioned in the beginning, we may have a different mean. So we can talk about bias because of the data distribution, right? We may have a bias towards one mean. We are training our regressor using target values that have a mean. And we don't know, for example, the mean of the target value for our test set. And as I look at the test set, I realized that it was selected in a way that distribution of features were completely different in some cases to the distribution of the features, I mean the columns, right, the variables in the training set. So this is a type of bias. This is a type of bias. If you somehow have a given mean for numerical features in your training data, and then for your test data and those numerical features, you have a completely different mean, this is biased. In this case, your regressor will be trained considering one mean. But when it has to be applied to the test data, you have a different mean for those variables. And your regressor may not find the right variables, the right predictions in an accurate way, right? So this difference of training data and test data distribution will definitely affect, in the sense of bias, the results of your models. So there is, and in this set, there is for sure some bias because we already saw that for some of the variables in those plots that I show.
Yeah, but maybe it's also kind of similar to data drift.
Yeah, this is exactly the same. Exactly. Yeah, yeah. It's in a different way. It's a lot of data drift, definitely. And this is something that happens. So in this challenge, this was manually curated somehow, but in the real world, we see this more and more. We see that the training data that we have for some of our classifiers, some of our procedures, is usually completely different to the test data that we have for real world applications. So we train a machine learning method with clinical data, for example, using a specific device for MRI. And then when we go to implement this for a given clinic, they have a different MRIs or they have different type of measuring devices. And this creates a data drift, right? This creates a domain type of difference. We have even different domains sometimes. And of course, models trained for a type of data may not be sufficiently good for a different type of data that comes maybe from different domains. So to us, it may seem, oh, but it's just MRI. But no, sometimes, for example, the type of resolution may impact and other type of characteristics of the imaging modality may impact. So we have to really dig deeper into how the variables are computed. So that's why we say sometimes that it is not enough to know the values of the data, but we also need to know the context of those data, how those values were actually computed, created. So we need to know the type of equipment that was used. We need to know when it was created. We need to know what the type of resolution that they might had before computing the feature. So there are many issues also that influence this. So that's why we talk a lot about improving the data so that we not only need data values, but we also need the data context. How was the data captured is something that is really important to consider, especially for these real world applications where there is a drift, as you say, there is a difference. So this is heavily studied in approaches for transfer learning, for domain adaptation, but it's a hard issue. It is something that is not solved, and I think it depends specifically on each type of application. It depends on the specificities of the application. What you can do to improve that, to be able to generalize your models, not only to test data that was not seen in training time, because that is now the easy case, but also on test data that may have been captured under different conditions than the training data.
I totally agree. Thanks for the explanation.
Thank you for the question.
Thank you.